Thanks for the introduction. Thanks for having us at Sussex AI today. I'm going to give you the theoretical motivation for this. So essentially, this is our 7th collaboration. 1 was a dog, 3 are humans. And this is the 3rd non-human or dog one. And this work comes out of some work we did previously in machine learning, philosophy of AI. So I've got the paper here. It's in Minds and Machines, Assembled Bias. So essentially, a while back, we were working at the time on connecting to this literature on algorithmic injustice, where people were talking a lot, especially like at the advent of philosophy getting into contemporary AI, talking a lot about how bias can infect AI. And there's a lot of work done on how human societal bias, gender, race, and other kinds of bias could impact AI and predictive models and output through the training set. So the idea being the bias is inherited from the training set, or even if those features aren't encoded directly in the training set for machine learning, there are proxy features. So say proxy features of zip code or area code for race in the United States, given various historical segregation. And so we were actually concerned to say, actually, with the use of machine learning, as wonderful as it is for finding these sort of hidden predictive patterns in the data, the inherent nature of it itself actually lends itself to exaggeration or bias. And this we called assembled bias. And really, it's driven by the idea of how these machines, so to speak, learn. And as you'll see in a second, we'll contrast this to how human children and humans in general, at least I'm a philosopher, so you have to forgive me, on a person level, on an agent or system level, learn. Okay, and so in this paper in particular, we worked with GANs, generative adversarial networks for generating images and discriminating images. And we talked about the fact that when you feed in the feature space for an image, say, the features that the system gets are features like the pixel shade, the pixel location. That's sort of the initial feature space, especially if it's black and white image. And from this, it's supposed to predict, say, and we later we'll go on to show you whether it's a spider or not, for example, and learn to generate an image of a spider. And, what's really perplexing is this initial feature space that you're giving it is not predictive in and of itself. So, of course, the really great thing about machine learning is what it does is it uses this initial feature space. It finds patterns among those features that are more predictive. And this is often called, we call it feature creation. People have called it feature learning, feature detection. There might be some other ways you've heard it labeled. But the idea is that you assemble new, more predictive features for the task based on the initial feature space. So you find the more predictive patterns locally in that feature space. And so on and so forth iteratively. And of course, we didn't talk about in this paper, but for large language models, you can talk about the token among the initial feature space. Okay, and so we talked a lot about how essentially what it's doing, so to speak, is zooming out. So it starts with this initial feature space, and it starts very locally with one by one pixels. We've got like pixel shade and pixel location. That's not going to help you decide whether this is a spider or not. So then it's going to form new predictive features based on patterns there. And then it's going to form more predictive features off the basis of the patterns of the initial features, patterns of features, and so on and so forth. In large language models, you can see this with using token embeddings to form layer 1 features and layer 2 features, this sort of progressing through the layers. Okay, and there's a lot more detail on this in the paper, the earlier paper, but I just want to set up the problem. You know, what we end up with is a predictive feature, right? So this final prediction or classification or next token, this is the last thing to be assembled on top of this sort of feature pyramid. Now, what's really important here is that the big picture, or the gist as we'll call it, is the result of this assembly. Just to give you an example, this is the example we used in the earlier paper. I was just ragging on Russ here because he used the picture that our eldest child drew as a kid. And our middle child actually is quite the artist, so she's not a great illustration. That's the problem, though, is that is the problem. Yeah. She's more like an image generator. But this is one, it looks more like an ant to me, that our very analytically minded older one drew. So this is a picture obviously drawn by a child. And if you ask a child, right, generate an image of a spider, or as you would put it, draw a spider. What are they going to do? The first thing they're going to do, if they know anything about spiders, is think a spider is a creature with 8 legs. That's what a spider is, right? And that is going to drive the process. And so you can see here, this looks like an ant, but it's got some cool features. It's an 8-legged creature, right? There's not a lot of detail here in terms of like the hair of the spider, or like the bendiness of the arms, things like that. Appendages, whatever they're called. But look, the big picture is perfect. It's this 8-legged animal, yeah? And yeah, we're missing the local details. This we're going to call the gist first, or big picture first process. And this is why I said, at least at a person level, agent or system level, this is sort of how we operate as humans. Now, if you ask AI to make a spider, you can do this with like combined large language model, image models, generate an image of a spider. What you get, and we had some images, but they were really older ones. You can try it for yourself. You get these very photorealistic, like skin crawling, creepy things. Like you can try it. Got this hair texture and these like very intricate legs. Maybe they are in a cool background. It's scary. It's creepy. These local details are perfect, right? Like you know, this thing would scare you. This thing doesn't scare you really. But the thing that I could show you, but you know, you can generate them. They're scary. Okay. The thing is, and this was a problem for a very long time. This is just one example, as we'll talk about in a second, of exaggeration or bias. The thing is, there's this big problem. They almost always generate spiders with more than 8 legs. Like, and in the paper, we kind of describe why that is, why the features that are attended to early in the feature learning or detection process are the patterns that are indicative of leg, even though it has no concept of leg, and how those are kind of spread out through the representational space and drives early on what's going on. But, you know, the system has no sense of it has to have 8 legs. So the spiders, they look like spiders is one way of putting it, but they're not spiders because spiders have 8 legs. And you can, just to contrast it with that earlier, you know, algorithmic bias that was talked about, it's not coming from the training set because you're not feeding in photos of 11-legged spiders. There are no spiders you're feeding in photo-wise that have anything but 8 legs, right? Indeed, the initial feature space is just pixel and pixel shade and location or whatever. All right, so this is the detail first approach that AI takes. Okay. Oh, and I kind of talk about this, all my shameless plugs. I kind of talk about this in a pop article in Free Clark's Daily about why AI is so great for science, but actually it's because it works as more like an artist. And this is part of the idea. Okay, so this isn't an accident. It's not an isolated case. It's a systemic problem or feature. It's both a bug and feature of machine learning. It's part of that assembled approach, including with large language models. So just the idea of the token or the pixel, this forces the model into a local first, detail first process. The big picture's lost. So the model's world is just this sequence of discrete arbitrary chunks, and then only the big picture is sort of like weakly inferred, right? As a statistical pattern, if it is at all, after the model has already processed these local features. It's a fundamental flaw. Now the idea is, in order to fix the spider problem, we could kind of hard code in like, don't make hands with, 10 fingers, or don't make spiders with 8 legs. But if you really want to fix the problem systematically, you can't just build a better assembler. You have to change the process itself. And this is what was sort of motivating us from this earlier work. And so we thought, well, there's this need to detokenize. So we're going to move away from an architecture that's driven by discrete tokens and toward one that can just fundamentally grasp the continuous underlying gist or big picture first. And as Russ will better adequately speak to than me, this is distinct from the many variations of continuous or non-discrete data structures. Okay. Okay, and you can kind of see like there are real world consequences of assemble bias in all of our models. Here's where I talked about it. It's almost Halloween, so I thought it'd be okay to put this. I don't know why I was in a dark place, had a very creepy image on this one. But this idea of hallucinating, right, is a major problem with AI models. And you can kind of see where this comes from, given what we said, right? More depth, more layers, it's more power for the model. That's great. Deeper models have more layers of assembly, incredible capacity to learn this complex, subtle, local detail. That's why they get the texture of the spider hair. But more layers also means more hallucinations. There's been tons and tons of work, of course, on hallucinations, whether we should even call them hallucinations, because that's human-centric. This comes at a cost, right? So if you got deeper models, it's more prone to, quote unquote, losing the plot. I was just talking to the students about this yesterday, about story writing with AI and kind of keep the plot, right? It's got great details, kind of keep the plot. So they confidently generate outputs that are often factually wrong, with legal briefs and things like that. Nonsensical, self-contradictory. You can ask them why, draw a spider. It'll give you an 11-legged spider. They'll say, here's a spider. And it'll say, no, it's not. Why'd you draw it like that? It has 8 legs. And it'll say, you're right. I was wrong. This is just all a measurable symptom of assembled bias or assembled features. We're not the first people to point out the sort of losing the plot idea. So here's one example. Studies on long context show that models literally get lost in the middle. They fail to use information from the beginning when the sequence gets too long. Okay, and so, what we really want is something more like the child's approach. You want to have the big picture first, and you want the details perhaps to be filled in secondarily. You want the big picture, the gist, to kind of be the global constraint. A kid can't draw an 11-legged spider. You would say, no, that's not a spider, right? The gist guides the details, not the other way around. So here's what we want. Here's the desiderata, as philosophers would say. What we want is a kind of mechanism that's gist first by its very nature. So we want a system where the big picture just comes first. The whole is stored in every part. When you lose the local details, that just blurs the gist instead of breaking it, like a child's drawing. And the gist can be used to reconstruct the details. So that's what we're looking for, just first architecture in AI. And as it turns out, this is the definition of a hologram. So this motivates, our project of the search for a new holographic framework for AI, one that builds from the gist rather than towards the gist, as they typically do. Okay, so that's me. Now on to Russ.
Sorry, I'm trying to make sure keeping track of time. Do you have do you have your phone?
Yeah. 17.
All right. So we've got like 1:50, 2 o'clock. Is that when we're 1:50? Yeah. All right. We'll keep it. We'll keep it in there. We'll be careful. All right. Right. Okay. So Robyn was just talking about how we need to work towards this holographic sort of thinking. The title of the talk is that attention is holographic, right? So are we done? Is all good there? Well, of course, the idea, as Robyn was just talking about, comes from this assembly, right? The attention part is just a small part of this larger assembly that we get when we're looking at things like transformers, and that's what's leading to the spider problem. So the fulcrum of what we're going to do for this part of the talk is to describe how sort of accidentally we have this embedded holographic component attention inside this larger assembled system that the architecture of these deep layers is still assembling on top of. But again, in a very real demonstrable sense, the attention mechanism supporting this is holographic. We'll go into some detail on that. And our task is to try to understand this holographic engine so that we can take attention, scare quotes, where it wants to go. Okay. So just some sort of key aspects of holograms that make them so attractive for us. First and foremost, what makes holograms really holograms is this distributed information, this idea that every piece of the hologram contains information about the entire scene, right? This is what makes holographic data storage the next big thing for the last 20 years. This idea that we can encode something holographically on a disk, we can scratch the disk, we can break the disk. As long as we have some chunk of the disk, we're going to have a blurry representation of the original signal. And if we don't, this is just sort of, we don't need to know a whole bunch of physics about holograms, right? This is just sort of, you just take it on merit, right? This is what makes a hologram. This is what makes it attractive for us. And because of this distributed information, it makes holograms particularly robust. As I was saying, we can scratch and blur them. And then we can reconstruct them by shining a reference beam back through it and reconstruct this crisp signal from the fuzzy signal, provided that we have just some chunk of the hologram because it's spread throughout. Okay. And sort of stepping back a little bit, even not thinking about attention specifically, obviously this is and I'm going to make a blanket apology here. I don't really know what the technical background of the room is, so I'm definitely going to undershoot and overshoot it at various points throughout the talk. But as far as like machine learning in general, right, this sort of these sort of features that we get from holograms aren't unique to attention in the sense that we would like them for machine learning more generally, right? Obviously, at a very basic level, anything we're doing for machine learning, we want it to be robust. We want to be able to handle noisy, corrupted data. And as we've sort of started to discover finally in the last decade or so, it's nice to have the architecture itself be redundant, be able to withstand scratches, so to speak. And as far as attention more explicitly, how it uses this distributed information in reconstruction. I'm sure we're familiar with attention at this point in transformers, but essentially its trick is that it doesn't just look locally, right? It lets every token interact with every other token based on a similarity score. And that gives us this notion of global mixing. So the output for one token isn't just about that token, it's a weighted blend of all the tokens. And that's what makes the basic level transformers sort of famously able to be reconstructed, right? We can mask words, handle noise, and like a hologram shard, we can get the gist from the remaining tokens. We can figure out what's in those missing tokens because that information is spread across tokens. All right, so sort of a quick outline of where we're going to try to go from here. Again, the main sort of crux of what we want to go do here, what we have in the title, is to show that this is not just a nice metaphor to have, that in a real definable, demonstrable way, this basic vanilla softmax attention from 2017, and then progressively more so as we go, is, and again, a very definable, demonstrable sense, holographic. We do this using what we call the plates framework, named after holographic plates. We're going to introduce this framework, use concepts from kernel methods like random features to approximate a standard softmax attention. And then crucially, these plates can reframe attention. The attention calculation is building up two stateful components, psi v and psi 1, that are going to be our holographic plates. And then if we have time, and I'll make sure that we keep track of that, we'll show how sort of the more recent advances in related to attention and transformers since 2017 actually fall out fairly cleanly from this framework once we start to represent transformers, attention specifically, holographically. And we'll try to make this a little more explicit as we go, but the sort of high level, gisty, if you will, idea here is that once we start representing attention holographically, we can go beyond just this simple sort of, we want it to be robust, we want it to be able to handle noise. We can say, well, if it's robust, if it can handle these scratches, can we start scratching the architecture itself in a way that keeps track of this blur, in a way that we can regain the signal and actually start to change the actual operator. And we show how using this framework, some of the more recent advances sort of fall out relatively cheaply from that. Then moving forward, as a former topologist, this is sort of what made me feel young again. I should note, because I'm going to talk about sort of topological type stuff, because again, I'm a former topologist and it gets me excited, but there's no actual topology in this. I think that's sort of a natural direction this could go. I think you could put topology on this. I think you could put a manifold structure and that could do some cool things, but we're not actually using any topological structure with this explicitly. Instead, the holographic representation is going to almost act like a topology on attention. And what that's going to allow us to do is make this trait here, where we can go from having a very complicated black box function mapping operator, whatever you want to call it, on this very, very simple space into a much more simple mapping on a much more complex space. So this trait is essentially, if we think of attention on tokens, if we think of those tokens themselves as being just the simplest possible space we could have, right? Just literally chunks of tokens. And even after the embedding, right, it's exceptionally simple space. The process on this space, though, of course, is the notorious black box that we can't, even the engineers working directly on it can't make much sense of, which is why when people in pop articles ask, why do these hands have 12 fingers, and they can't give you a solid answer, because they don't know, right? This is, again, just an obviously very, very complicated process on what is ultimately a very simple space. What we're going to do with this, in as much time as we have to do it, is map that into a more simple, much more simple mapping on a more complicated space, so that complication, all that complexity is being put into the space itself. But this is a good trade for us, because even though that space is decidedly more complicated, I have complex here, not complex as in imaginary numbers, but complex as in complicated. Even though it's a more complex space, we can show that it's a nicely structured, very well-behaved space. We can put literal coordinates on it, and it allows us to navigate through much more cleanly. And importantly, for what we want to talk about, this new space is continuous and, in a very real sense, token-free. So then if we have time, well, I guess we'll make sure we have time. We'll talk about some quick wins we can get from working in this space directly. We'll look at what we're calling principal efficiency here, which is just really a reframing of something we already have. We'll talk about that if we have chance. But again, the important thing, given Robyn's introduction, we want to build towards, again, scare quotes, this in-mechanism detokenization, and this is easier to show than to tell. So we'll spell out what we mean by in-mechanism detokenization as we go forward. All right, and then the not so quick wins are not so quick, so we will get to those if we have time. All right, so getting into the meat of this then, actually formalizing attention with plates. This is where we make that sort of metaphorical holographic, these are nice properties to have, we want them, and attention already kind of has them. This is where we start to get explicit and say, this is not just a metaphor, this is an actual holographic structure that approximates vanilla attention. So I'll point out here, the other thing to take away from this slide is this bottom part where we talk about sort of this large language model. We take the text, put it through a tokenizer, embed it, and then at this stage here, where we would use softmax, the actual attention stage, this is where plates live, right? We're approximating this softmax part here. Note that this is coming after the tokens, right? So when we talk about detokenization, this is hinting at what we mean by in-mechanism detokenization. It is not, as Robyn was alluding to, just we're gonna put in continuous data, essentially, right? That's not what we're doing here. Okay. So the core idea then is to find this feature map such that the standard vanilla attention kernel can be approximated by a product in this feature space. This, I don't have a pointer on here, but this feature map is doing most of the heavy mathematical lifting, so naturally we'll just breeze on through that. We want to get what we can get, and we're going to link to a paper that has more details on this if you want to look into it. But what we want is this bottom part where the vanilla attention mechanism is represented by this inner product. From there, we can just replace that attention mechanism with that inner product and write attention approximately as this, and then rearranging this, we get what we're calling the plates factorization, where these parenthetical sums are going to wind up acting as our holographic plates. So that's the part that we really want to keep track of. But again, not to sneak this by, right? We still keep the queue for query. We haven't detokenized this yet, right? We're still interacting with the tokens. So there's more work for us to do. But then again, yeah, the separating those plates, we get what we're calling the value plate and the normalization plate. Again, we're borrowing this directly from holographic optics. And this is not super important for what we're doing to note this, but I think it's cool, so we're going to note it. If we treat these as essentially, and again, sorry, I know that I'm going to be very hand-wavy on this, but it is in the paper. If we treat these as essentially Riemann sums that we're going to try to make, we think of these as making these smaller and smaller until they're essentially infinitely small, and we're in the continuous setting theoretically, right? If we do that, we can show in that limit that we get an actual hologram with actual interference. So in a very real sense, this approximation is holographic. And although that's not super important, something that is important to notice this bottom part, that these are fixed size tenders that are only depending on M, the features from that original feature map that we talked about, and D model after the embedding. And it's independent of the sequence length T of tokens. Okay. So then, yeah, just putting that back in, calling this a plate operator, where we put that back in what we had as with the explicit plates representation, and add a small stabilizer on the bottom so that we're not dividing by 0. Okay. So the key result from all of that is that this plate operator approximates the original softmax attention, and we say approximates. That's simply up to the feature map and dimension of M. If we take M up to infinity, this limit becomes exact. Or sorry, if we take this limit as it goes to infinity, this approximation becomes exact, right? So in a very real, again, demonstrable sense, this softmax vanilla attention that we're building after we put the tokens in can be represented in this holographic way, where again, if we take those as the limit, we're getting actual literal holograms. All right, and so yeah, we're doing pretty well on time, actually, so let's go through this. So a couple of, I'm going to stop before I get ahead of myself here and point out, if we're familiar with the literature, this I'm sure would have been pointed out to me in due time anyway, but these next couple of slides are not our results, right? These, if they look very exciting, they are very exciting. Unfortunately, they're not ours. We're just trying to make the case that looking back anachronistically with our 2020 vision that we have, using the plates framework, these sort of cool results fall out fairly naturally. So the problem when we first had vanilla attention was just, it was very expensive in terms of tokens, right? Each token has to query every other token, so it's quadratic in terms of tokens. But if we represent it using these operators, these plates, psi v and psi 1, this would tell an engineer the framework saying that the operator is just a query against these plates, right? So we can just find a fast way to approximate the plates directly. No better way to do that than random positive integers, and from that, performer falls out, right? So this is, once we start thinking of these holographically, these sort of computational fixes fall out fairly naturally. This one is not quite as natural or direct, but I like it, so I'm going to try to go through it anyway, and we'll take a little leap of faith if we can. But this problem, because it's going to be important for us, how do we positional info robustly? So we have from these plates a global summary that are creating a single fixed summary of the entire sequence. And for the query's interaction with the global summary to be meaningful, then across these absolute positions, we need the query to be summarized regardless of where they appear in the sequence. So this would point us to positional info that depends on relative structure and is stable under shifts. And then it's a little bit more of a leap to get to rope from here, but it's not ridiculous to think that how we would then get to that, right? It's kind of a clean way to do it if we're familiar. would be this, the actual articles, this is from 2024, but it's been in the field for a few years before that. These so-called rope embeddings, the rotary position embeddings, and before that, the sort of similar self-attention from the relative position. And then this one, if people are practicing on this, I might embarrass myself by saying I don't know of anybody doing this. For all I know, it's actually being done extensively now. Not when I say this, I don't mean dropout. I certainly know that's extensively being done. This is in some ways super anachronistic because we're talking about dropout. Dropout predates attention itself, so certainly predates our holographic representation of attention. But so for familiar with dropout, the idea is essentially we want like we were saying with holograms in general, right? This holographic property, we want the system itself, we want the operator itself to be robust, not just to noise that's being fed in as data, but to, so to speak, scratches within the architecture itself. And that's the idea of dropout, right? It was posited about 10 years ago as a way to deal with overfitting. But the essential idea is you're taking out parts of the architecture. In 2014, when this came out, that would have been, right, neural networks pretty explicitly. You're taking out nodes, but whatever it is, right? You can apply it very generally, literally taking pieces out, training on top of that, and then putting them back in, sort of forcing it to be robust in that way, right? And I'm pointing this out here because this is certainly being done in the transformer architecture more generally, certainly in the feed-forward networks that are being put on top of it, dropout is being done. But one nice thing you get from the place representation, right, is you're representing with these plates, so you're representing with these features, and you can start to do dropout at the level of attention itself, right? We can start to take away these features, and we know because it has this holographic property, we're going to keep that robustness. And it's not actually in this paper that we're going to link, but it's going to be in a companion paper where we show more sort of empirical results like that. And I point this out because I actually don't know, you can't do this cleanly with vanilla attention. It's worth noting you could do this with something like Performer, right? There are kernel representations. But as far as I know, it's not really being done. I just don't think people are thinking about Performer in that way, right? They're thinking of it as more of a straight computational hack. Part of the point of this is to say, look, if we start thinking about it this way and we start representing things as a hologram, we can start to see how these things can become more of a robustness hack as well, if you will. All right, and then to actually get into that space we were talking about where we're going to do something pseudo-topological and map from one simple space to a more complicated space and get the trade-off in simplicity in terms of the operator itself, we're going to need to define the class of operators that we're doing this on. We're calling this the class C. And the 4 conditions that we need for this are the positivity, output value is non-negative, row stochasticity, where the influence weights sum to 1, continuity, and then the important one, the more difficult one, I guess I should say, translation equivariance. So we need the operator primarily to depend on the relative positions between inputs, not their absolute locations. And so as far as C, are we being too restrictive? When we look at C, and I would contend no, we get 1 through 3 essentially just from vanilla attention. We don't need to worry about it. 4 is a little less obvious of a given, but with the more modern positional encodings that we're using, this is becoming more standard in the field. So this is I would argue this might be too strong a statement, but the actual operators we care about are going to be in this class C at this point. Okay. And so then assuming we have an operator in this class C, we can analyze scare quote physics using some functional analysis. So we're going to take the Gateau derivatives on the plates themselves. And from this, we're going to get our orthogonal axes that define the behavior. So again, I'm not going to go into the space itself. It's a little more complicated. It's not ridiculous, but it's not sort of straightforward, Riemann nice space. But we get these orthogonal axes that we can use as at least a local basis for this space. And these axes sort of loosely correspond to, you can, I think in the paper we have out, it will give them some more detail. If not, then the companion paper will. Call these the S-axis, which loosely corresponds to blur and gist. This measures robustness to noise, how much the output change if we blur. What we call ferrocinated in the paper is essentially just dropout. The U-axis, which is essentially going to measure stability and efficiency using these plates directly. How robust is it to the output of independent perturbations of content versus normalization? So this relates to computational efficiency as well. And then the C-axis, which measures positional awareness. So it looks at how output changes if we shift the input's position or phase, and a good operator understands relative structure. Okay. So again, these are, at least an expectation, these are orthogonal, so they actually do form a basis of the sort of well-behaved operators that we want to look at. So again, an expectation meaning just if we poke them all along the S-axis, for example, we add noise, it doesn't systematically affect what's happening on the other two axes and vice versa. So we can look at them essentially as coordinates of this space. And it's this, we can call it Sussex space after the three axes that define it. This is what's giving us that crucial trade-off, right? From the complex, opaque black box on a simple but unstructured space into this much more structured, albeit more complicated space where we have this very simple mapping that we get from the functional analysis. Okay. And so the main upshot of this space is that once we have operators mapped into this space, right, something we talked about is using these sort of, because this is underpinned by these holographic principles, we can mess with the architecture of the operators themselves, right? So this is just, we're going to get into specifics on this as much as we can. But again, sort of the high level idea of this is, again, because this space is underpinned by these holographic principles, right? Any operator that we can map into it, we can start messing with the architecture of that operator itself and still keep the general signal. So I'm going to give a very specific example of this that I'm going to call Sussex in honor of this talk. And a sort of crucial thing to keep in mind when we talk about this is this is by no means meant to be the end goal, right? The sort of overarching point of this part of how we're using this space is that we can use this space to guide how we're going to treat the operator itself, right? So this is just simply one way we can use it for a very specific purpose, right? It's meant to be sort of a specific baby step towards that end mechanism detokenization that we're talking about, that not relying so much explicitly on tokens. So all this does is we're going to monitor the holographic signatures as the token updates the plates. And then if the state remains stable across several consecutive token updates, we're just going to collapse each of these into an aggregated step. So the signal that we're trying to preserve here is this final plate state and the resulting attention output, which we're measuring again via this plates architecture and within that larger space. So how does that help us? So first, some nuances as a former pure mathematician. We'll note that this does rely on ordering to make this work, which feels, especially if we're talking about like a large language model, right, somewhat arbitrary, maybe not totally arbitrary, but probably a bit arbitrary, which bothers me as a former pure mathematician, but we'll see why it's still useful anyway. And we'll note that this is, at worst, a computationally cheap local check on the existing sequential mechanism, right? It detects local stability just based on that first pass through, and then any savings that we get is coming in at the much more expensive step. Okay. So this is essentially what I said there. This is going to be an efficiency enabler. And I'm trying to sort of step back here and point out where this is specifically useful is for something not necessarily like a large language model where tokens are fairly natural, but for something where we have inherently sequential data, specifically anything we're thinking of that's temporal, right? What motivated this originally was neuroscience stuff where we're looking at brain signals. And a big problem with trying to represent brain signals and try to take advantage of the transformer architecture is that any way you want to try to tokenize brain signals, you're going to inherently lose some information, right? This is a big problem for people who are working on it, just trying to figure out how are we going to tokenize it, right? An obvious sort of, if we're not worried about computational cost, an obvious fix is to just make those tokens absolutely, and by small, I mean, these are literal time segments, right? We're looking at the actual brain states as they go through. So when I say make the token small, I mean very small time intervals, right? If we get infinitely small, we're done, we detokenized it, we have the continuous signal. We can't do that, so we want to make it absolutely small as possible. The problem with that, of course, is that even with linear attention, that's going to get very, very expensive, right? That's, we're making precisely the most expensive part of attention the biggest part, right? That's going to get very, very expensive. But the actual update path here is very computationally cheap. And if, oops, where'd I go? Yeah, right. Yes, okay. Sorry, so the part where we're doing the actual collapsing is very, very cheap. And the savings that we're going to get potentially where we're having these tokens, if we made them very, very small, we can collapse them in such a way that is preserving the gist how we want it to be preserved, right? And then potentially have those savings, right? We can have essentially more natural tokens, more natural splits that are preserving the gist while not having them be incredibly small, right? That essentially it's going to make it exactly as big as it needs to keep the signal that we want to keep, right? So put more cleanly, it provides the most benefit precisely where the token paradigm is weakest. Okay. So I might be underselling it a little bit to say this is explicitly a baby step, but again, this is part of the point we want to try to make, right? That this is not what we're ultimately trying to go towards, but it's a clean, easy incremental step that we can get from this architecture. And it shows that we can leverage the framework within the existing architecture. We don't have to completely tear down transformers in order to get benefits from transformers. And importantly, it gives us some sense of this end mechanism detokenization, right? We don't have to pass in something that's explicitly been detokenized. The mechanism will itself detokenize it as it needs to. So Sussex modifies the attention computation itself to be less dependent on these tokens, and we're modifying the architecture to the input instead of vice versa. This is easily contrasted then again with stuff like continuous inputs or where we're trying to detokenize at the input level. These are, I've listed a couple there, but these are sort of a dime a dozen, so you can take your pick. This is, sorry, check on. All right, all right, I think I'll try to wrap it up in the next 3 minutes or so. Yeah, so let's see. I guess I should point out, this is again only using stability. We haven't really taken advantage of the orthogonality of the space yet. The other axes can offer ways to help, for example, with that arbitrary ordering that we were talking about for applications where the ordering isn't so natural and temporal. This is sort of what we talked about before. All right, so I think I'll just sort of give this was intended to be sort of a lead into something else, but I think I'll just have it be our sort of recap for what we have, and we'll leave it at that since we're right about the 50. So when we think about attention as a hologram, attention already, because it has its holographic properties, sort of naturally exhibits these hologram-like robustness, graceful degradation properties. Information is distributed. So like the physical hologram, minor scratches tend to blur the output rather than break it. And this is what makes attention as robust it is. Going further with it, trying to leverage holographic properties more through the plates framework. We can go further and intentionally try to take advantage of this robustness by affecting the architecture itself in these sort of controlled ways, with things like performer dropout, and then for one that doesn't explicitly exist already, what we described with Sussex. These are ways to engineer the system based on the knowledge that its underlying structure is robust and can handle these changes. And I'm going to, I think, not try to get into that, and I will leave it there.
Thank you very much, Robyn and Robyn. Do we have any questions for our speaker? We've got about 10 minutes, so time for questions. Like Ron was Just one of them.
Sorry, is it?
Yeah. So Rob's online, you can go first.
Is that all right? Thank you. Yeah, really interesting talk. I wanted to raise, can you hear me okay?
Sorry, we can't now, Ron, yeah.
All right. Really interesting talk, thanks. And I wanted to just bring up something that was in the motivational part when Robyn was speaking. And it might just be I was distracted and missed the key point, but I followed everything up to wanting to have a gist first based approach. And then there was a switch to, and again, I might just be asking you to repeat yourself. There was a switch to a desire for continuity rather than discreteness. And I didn't understand why gist first would be more allied with a continuous feature space rather than a discrete one. So if you could just explain that.
I'm gonna hand that one over to you.
Yeah, so essentially, I think the best way to talk about that is there's nothing sort of inherently in the discrete aspect that's going to stop you from being sort of just first, but practically it becomes very difficult, right? When you're trying to keep the big picture, trying to work in that discrete space, it becomes, and because that discrete space is inherently so simple, trying to keep the big picture through the mapping itself has to become inherently very, very complicated, right? To actually start working towards having a gist first that it can sort of keep as it's progressing through, it's much simpler to try to have a simple sort of mapping on a more complicated space so that that space can hold the gist itself. And that inevitably is going to lead to more sort of continuous space that you can work in it more simply, if that makes sense.
Okay, I'm not sure if I quite have it, but is there any way you can motivate it in terms of the spider example? So is it easy to explain why continuity would help get the right result in the spider case, or is that not going to be a useful example?
Not super easily, because that's essentially what we're sort of trying to work towards. But the short example, I guess the sort of high level answer that's not getting into the nuts and bolts, because we can't really get into the nuts and bolts because the nuts and bolts are too hard.
Yeah.
If you can map an operator of the spider, right, where you're looking at okay, sorry, let me step back for a second. When we're looking at the spider, as Robyn was talking about it, right, where you've got these individual pixels and we're combining them to make these new features and everything, right? We want to be able to map that representation into a more global space, right? Which is the idea behind trying to map things into the Souk space, so to speak. And then we can change those representations themselves, right? We can start to move around the weights and how things interact with each other by moving them through this continuous space, right? That's going to give us that sort of, that's going to allow us to keep that big picture sort of gist while we're trying to work out the specifics, if you will.
We do
Thank
have
you.
a lot on the spider example in the context of assembled features and actually a visualization using topological data analysis of what's going on there in that earlier paper
Mhm.
that we started with.
But that's kind of looking at
Previous,
the,
yeah.
Oh, sorry.
And do you have a working code example?
I'm currently doing that. I'm gonna have a companion paper. So I have a theory, I think, yeah, we link it there.
This.
This is not the working coded example. This is the sort of the math aspect of it. And then, I'm currently working on a companion, like Python code output paper. Yeah. Yep. Sorry.
Okay, yeah, I must admit, I got a bit lost there. You were detokenizing. You had a
Fair
slide
enough.
where you're actually saying, oh, like I start with these tokens.
Yeah.
And then here's a step, and that looked a lot like stochastic sampling of the token space to make new features, or was that not the intention? How you detokenize? How do you get to that other space? I think you just almost yeah,
Yep.
this line of things there, right? So you have to embed, and then
Mhm.
what makes the plates, and what transformation is that? I mean, what
So what makes,
this takes you into the plates, right? And that's you actually this continuous space you're talking about, or maybe
Right.
not.
So plates itself is not the continuous space, but it's going to allow us to get into continuous space via the functional analysis. But what's getting us into plates itself is this here, essentially, not essentially, this here. Where we're taking this feature map and then just getting that. So it's essentially, if you're familiar with like kernel methods and feature maps, we're starting with that, right? That's doing the sort of the hard work of the actual math here. So something like performer, and then separating like this, and then where we're actually getting into the continuous aspect is just to note that this can be thought of as a hologram, right? We don't actually need that for what we're doing, but once we know that, then we can start doing, I've lost it again. No.
So is it the old kernel? And is it in terms of representations where you get into, is it the old kernel trick in the end? Yeah.
This, yes, right. But that's what's going to lead us into this. Is doing the functional analysis on that. And this is, again, sorry, this is, if you want more detail on this, I'm trying to kind of get through this in the interest of getting through the talk, but there is more on that in the paper itself, but where you can actually see where we're getting the functional analysis from on this. Yeah.
Don't the wider class of neural network layers have this holographic property, like an NLP, right? That distributes information everywhere. It's relatively robust to noise.
So-
Is this unique to?
Oh, I doubt it. I agree. I doubt it.
I think you're saying that attention is kind of the one bit of this architecture that isn't this bottom-up building, but these holographic properties don't seem to be what separates it.
So I would absolutely agree that these holographic properties are, whether intentionally or not, right, in a lot of what we're doing in machine learning and AI, right? Like I was saying, these holographic properties are just inherently things we know we want. We're going to try to get them, right? It's entirely possible that if you start exploring some of the other stuff more explicitly, you could start to make representations like this as well, and that would be cool. I don't know if you can get it as explicitly, right? I mean, maybe. I don't know. I haven't done it.
Any more questions about this? Okay, let's thank everybody for the end.